So the last lecture we already started saying, so what we're interested now is trying to find a way to systematically derive effective theory. So what we did so far was perturbation theory, but we said that we did something very specific, which was perturbation theory around non-interacting reference point, and this does not always have to work out. So we need some more general scheme. And the scheme actually, we've already formulated a 5-step program that we are going to follow how to derive effective theories. So, which consists, the first point is just give like brief summary. So identify the relevant structural units. So what is meant here is to do exactly what we have done so far in the perturbation theory. It's always a good starting point to look diagrammatically what is going on, and if using the large parameter that we assume to have in the problem, we can identify certain classes of diagrams that will dominate. This can be due to phase space arguments like we encountered. So this means that once we have identified certain blocks of diagrams which are relevant, this then allows us to see what will be a clever way to introduce a new field, which is a composite object of the microscopic degrees of freedom. And this we will discuss in detail today, like how this is done and what are normally the possibilities, how to introduce this field. Then, once one has introduced the field, one can trade the microscopic degrees of freedom in which perturbation theory was formulated for in terms of an effective theory in this new field. So this is known as the Hubbard-Sartonovich transformation. This we're going to discuss in detail. So the way one integrates out the microscopic degrees of freedom to derive an effective field theory for this new physical, let's say, physical field, in the sense that this is a field which we think captures nicely the relevant physical degrees of freedom. Then once one has derived this effective theory, one can subject this to saddle point analysis. So there can be cases where the saddle points are just trivial, and this will be encountered in the case of the plasma theory of the weakly interacting electron gas, which means just that the non-interacting reference point was fine, so one didn't have to worry. But there are other cases like magnetism or superconductivity where this doesn't have to be the case anymore. So where one finds a finite mean field, and this would mean that any perturbation theory around the non-interacting reference point would just lead to inconsistencies in form of instabilities. So this can be an important point, finding the right saddle point. And then one can just consider fluctuations around the saddle point, which will then be the effective theory. So this is then an approximation, like the steps up to here are all actually exact. So the saddle point analysis gives us some hint on if there's some phase transition or whatever occurring. And then one can derive in a systematic way the theory and fluctuations. So first, like Gaussian fluctuations, then include interactions and so on. So this is an approximation, but which should be well controlled. Okay, so this is a 5-step program that, in the best case, so in the first case we will consider how this works for the weakly interacting electron gas. Then we will discuss another example, but in the best case one would then discuss several examples. So if we are going to continue, so probably we'll discuss. Okay, for sure we'll discuss the weakly interacting electron gas. I also want to discuss one case of magnetism. Then the next big chapter would be to follow this program for superconductivity, and another bigger block would be to study this program for disordered systems. This would be something one can do. So then, once one has a feeling like how these effective theory rise, like see like what are examples of non-trivial saddle points, then the next big block which one should discuss is an RG analysis of these effective theories. So with this one has already covered a lot of things. So then from there on we can then study like effects of topology and so on. But once one has discussed the effective theories with examples and the RG, I think then one has a big like how do you say caixinha de ferramentas with what you can address a lot of problems. So first we want to follow this program for the plasma theory of for the interacting electrons, so the interacting electron gas. So I just here recall the action that we already discussed, which is the electrons with quadratic dispersion, Matsubara frequency, and an interaction term where the interaction is given by the Coulomb. Their Coulomb interaction here, I use the notation of the formal method. So this here would be what we call the interaction part of the action, and this is what we call the free action. So let's just make some general comments and then see how one can introduce this new field. So this we'll discuss in detail then. Just make some general comments. So, well, what one is encountering here is a problem that if the interaction wasn't there, one would have a quadratic series. This is exactly solvable, but due to the interaction, due to the quadratic term here, there's no possibility to do an explicit integral over the electron field. So no explicit calculation of the electron integral, so psi integral, is possible due to the presence of interactions. So the interaction term is a quadratic term c bar c squared. So the idea then is, since one cannot do the exact integral, one can try to what is called decouple the interaction term, and this is what I'm going to explain. So however one may decouple the interaction term, and the idea is to exchange this quadratic term, which here is here and does not allow for an integral over the fermions, to exchange this for a quadratic term in the electrons, coupling to some field. But this field then has its own dynamics. So once one has done this, one has a series of quadratic electrons coupling to some fluctuating field. But the quadratic sphere of the electrons is then Gaussian, so one can integrate over the Gaussian field, Gaussian fluctuation of the electrons, and arrives at some effective theory for this fluctuating field. And this fluctuating field should be introduced in a clever way, such that it knows about what we think are the relevant building blocks of the theory. They're all the physics entries, okay? So that's the idea, and technically this can be done in the following way. So one introduces a representation of unity. So one just writes the one operator in some complicated way as a field integral over some Gaussian field, which is here, then should be clear the motivation once we have done some manipulations why one introduces this in a very specific form. So here's some prefactor, don't care too much about, it's just using for convenience in this way. And there I also will discuss there is some freedom how to do it, but this would be one way how to do it, and it should be clear why one do this. So just introduce some trivial or some complicated representation of the unit operator. So here the phi is a complex bosonic field. And since this is 1, we have just hidden all the normalization factors in the measure. Okay? So this measure includes like the determinant of this operator here. This is just for convenience here through this way. So the normalization constant measure. Measure. And then just to recall, so here now we use again 4 momentum. However, in the omega n now some bosonic Matsubara frequency, and this is again the 3 or d-dimensional vector. Okay, so this is just a complicated way of representing the one. Now the idea is to make here a shift in this variable. Okay, the shift doesn't affect the one here, but we can shift it, and well, the idea is to shift this in a clever way. You see here is already appearing the v to the mass. So here's depending, this is the potential. So this is written for convenience this way. We would see other ways, but the idea is to shift this in a way such that we can get rid of this term here. Okay, I just write it down, then it becomes hopefully more clear whatever. So the idea is to make a trivial shift which doesn't affect the integral being 1 in the following way. We shift phi q by phi q plus I over e theta, e of q, and then some rho of q, and this rho is just the density at a finite momentum, so it consists of the summation over 2 electron hole actually, sigma. Okay, so this we shift in this way. Okay, so why do we shift this in this way? Well, there will be appearing then 2 terms. One is where phi of q couples to the rho of q. And then there's a second term where rho of q couples to rho of minus q. Now this comes with a bq squared, so we get here v of q, rho of q, v of q, rho of q, and the prefactor is actually chosen exactly such that we will get this term with the opposite sign. Okay, this will cancel this, but I write it down in more detail, and then just we'll come back to this point why we introduce the rho exactly in this form that it's a density. So there we'll discuss there's different ways how one can shift this field. Now, if you look at this, this is actually what we always encountered in these bubbles, no? So this would be what we encountered in the polarization operator, no? So in a way, we shift here the bosonic field that we introduce by some bosonic field, which is exactly the, let's say, the unit that we always found in the diagrammatic derivation. So this is only example. We'll discuss like more carefully why this works this way and what are other options. But just to already point this out, that this rho of q should remind you of something that we found over and over in the diagrammatic derivation. So, but so far, let's just take it as a mathematical, exercise, and then go to details. So, if we do the shift, then we arrive at the following. We can write the one in the following way. So, we have the 1 representation of 1 as a field integral over some complex field, which now has the action S of phi, which looks the following way. S of phi. So if you plug everything in and take into account the prefactors, you should find the following. So this is just copying what we had in the beginning. Now due to the shift, we get one linear term of rho coupling to phi. And then we have a second order term in rho, and this is given by this expression here. Okay. So, and all the motivation, which I already said, why we should do all this trick of introducing the unit in this way and shifting this, is the observation that what is written here, if you take the prefactors and everything, this is nothing but the interaction term. Okay? So the interaction term has here pi plus p plus q, and the p, which with this sum over sigma in p gives you one row of q, and then there is a p prime minus q, and p prime is sum over sigma prime. So this sum will give you a row of minus q. Okay? So this is exactly what is written here. So now if we let's see, I'll just continue here probably with this here. So now if we take this unit and multiply the partition function, which was in the beginning written as a field integral over fermions, which have a quadratic and a quartic term, the interaction, this can be written in the following way. So the partition function we started out from is the partition function in terms of field integral over the electrons. Okay? So we multiply this now by the 1. So this is 1 times c e to the minus s c bar c. So this is what we always considered. No? This is the action of the interacting electrons, and we just multiply it now with this representation of the unit operator. Okay, so now we insert this representation of the unit operator that we introduced here. And if we do so, we arrive at a representation of the partition function in terms of a double integral, so the integral over phi due to the 1 and the integral over the electrons. So these always here square brackets. And then we have an action, a new action, which now depends on the electron fields and the new introduced bosonic field, and I just write down the action where this new action has the following form. So it consists of 3 parts. So first we have the part which is this one here, quadratic theory of the bosonic field. Let me just write down this. Beta A P out to the Q, integral over Q, phi of Q, and I insert like b to the minus 1 is just the Q squared. This is for prefactors for pi and so on. So minus Q. So this is this term here. Then we have the part of the free part of the electrons. Okay, so I write let's say here we have some more p sigma minus my omega n plus p squared over 2n minus mu. So this would be just the free part of the electrons, but then we also have the part where the electrons, is the density, coupled to the fluctuating bosonic field. So I can include this in the quadratic action of the fermions here, and this, if you look at the prefactors and everything, gives you the following. Sigma. Okay, so this now takes care of 2 factors. First, the quadratic theory of the electrons, and then the coupling of the density of the electrons to the fluctuating field. Okay, and then there is, well, the density squared term, and then there is the force, or order term in the electrons. But we exactly, made all this trick, and we made the shift exactly in the way that these two cancel each other. Okay, so the entire game is exactly done to start out from an interacting theory in the fermions, to introduce a new degree of freedom of bosonic fields, which allows us to represent the interacting electrons as a theory where electrons couple to some bosonic degree of freedom, which now has its own life. Okay? So actually this is just a very trivial identity. So if you would integrate here out the quadratic field phi, this will just reproduce the action there. Okay, so we're doing, in a way, reverse engineering of some simple Gaussian integral. Okay? So this is known as the Hubbard-Sartonovich transformation. And let me just comment a little bit on the structure. But the idea is just very simple. We have a theory which is quartic here. We don't know what to do with it. So let's do a reverse Gaussian integral, introduce a bosonic field with an own life, and now the electrons coupling to this bosonic field. Everything is mathematically it's just an identity, except, okay? But the idea behind all of this is that, well, this phi should be chosen in a clever way, that this knows about the low energy content of the theory that we're interested in. And for this, then we have a controlled way to derive an effective theory. Okay? So we see now already we have a theory which is quadratic with the electrons. So in the next step, so let's first comment on this, but afterwards we can just integrate here over the electrons and have then a theory entirely in the phis. Okay? And these phis have to be chosen in a physical way. So mathematically, this is all simple identities, but let's say the problem or the art is finding the right phi, which then allows one to derive an effective theory. Okay? So to do this clever, that all this leads to some nice way how to derive an effective theory. So let me just first give a different representation of this effective theory here, or not of this theory where the electrons couple to the bosons in real space. So using the following convention for the Fourier transform, so the phi of Q is a Fourier momentum, can be written in imaginary time in real space, d-dimensional coordinates, using this kind of convention for the Fourier transform. So if one uses this Fourier transform, definition of Fourier transform makes here the Fourier transform, then one arrives at an alternative imaginary time and real space representation, which is given by integral over imaginary time and r-dimensional space, and what is the part in del. So this, I just use short form, this is always a gradient, yeah? Delta. And then, so this would correspond just to the Fourier transform of this one here. And then we have the term for the electrons, so we have the sum of the spins, sigma, time derivative, gradient squared, minus phi psi sigma. Okay, so one sees if we do the Fourier transform here of this, you see this is like a convolution, no? So convolution in momentum space becomes a local term in real space. Okay, so we get a nice local action consisting of an action for the fluctuating field, bosonic field, and the term where the electrons just couple to this fluctuating field. So and if you look at it, you can immediately recognize what this is. So this phi here just couples through minimal coupling of the time derivative. No? So this is the form that this can be the electromagnetic potential, but then the phi is the electric content of this electromagnetic potential. In general, there could be also vector potential, but this is like the coupling of the electromagnetic content of the electric content of the electromagnetic field, just minimally coupled to the electrons, and this is the action of the electric component of the electromagnetic field. Okay? So, but this is then just saying that, well, we can understand the Coulomb interaction between the electrons as the exchange of some photons, okay, which is here just the electric component of the electromagnetic field. So they just exchange the photons, and in a way we just did reverse engineering of this Gaussian integral. Okay? So let me just write down. So this here is Lagrange density of electric component of electromagnetic field. Okay, I did some abbreviations here. So Lagrange density of electric component of EM electromagnetic field. Yeah. So there could be the scalar and the vector potential is just a scalar potential. And this here is said just this like minimal coupling of electron density or electrons to fluctuating photonic field, which we say is the scalar potential, okay, or scalar potential here, just as a short form for the electric component of the electromagnetic field. Okay, so just try to write in short words what we discussed, yeah? So this is what we arrive at, and well, so far it's just a simple mathematical identity, that we did. But we write down some comments. So if we look, it's not enough space here. So in the best case, it would have been like the 4 steps. So I don't know, it was the first step, identify the relevant structural unit. I didn't comment on this, we will comment on this, but I gave you the hint that the row that we introduced that the phi we shifted by a row which was exactly the polarization operator, that appeared. So this is in a way like was the first step, the relevant unit. But then the second step was introduce a bosonic field, and this is like the second step. Well, okay, I don't remember what was steps, but we're in step 2 or 3. It's not written there anymore. Okay, but so we have completed step 2 or step 3, I don't recall. But this consisted in trading the theory of interacting electrons for a theory of non-interacting electrons in some fluctuating field, and the fluctuating field has its own dynamics. So we have succeeded. To trade theory of interacting electrons or theory of non-interacting electrons non-interacting means just quadratic theory in the Turing field. However, these non-interacting electrons are in the fluctuating field. You can think of the photons transmitting reactions. Where the matter, so this fluctuating field has its own dynamics. And it's also described by quadratic theory. By quadratic. Okay. So questions, or so far, I mean, just a simple mathematical manipulation. It's not so clear why we chose the row like it is, but we'll come back to this, okay? Questions, or? Okay, so let's just make some little statements again. So what we have done, so this is what we call the decoupling, like the reverse doing of a Gaussian integral. The above decoupling procedure, I mean, again, it's just, in fact, like mathematically, it's just a simple Gaussian integral, but it has its own name, and it has its own name because it's a very important step. Like, if you put physics contents into it, and it's an example of what is called the Electron-electron transformation. This is one example of famous Electron-electron transformation, and I will just do not write it out. I will just call it HS, Electron-electron. And we have done this here for the case of the interacting electrons. So as already said, where we said, well, this just states that we can see that instead of looking at the electrons interacting with via Coulomb potential, you can understand it as electrons in some fluctuating bosonic fields, which is just the photons which transmit the interactions. Okay. Okay, but you can actually formalize this to a very generic case where you don't have to consider like electrons like we did, and just any kind of quartic interaction which can be between fermions or bosons, whatever. This is just what we're going to do now. Let's just try to generalize a bit what we have done there. Okay? So Hubbard-Satonovich transformation in general is, we want to generalize this, is the decoupling of an interacting theory. Interacting theory means quadratic theory plus a quartic term, by introducing some bosonic degree of freedom, which then allows to write the interacting theory, quadratic plus quartic term, in a theory which consists just of two Gaussian theories, like the auxiliary Hubbard-Satonovich field and the original field are both quadratic. However, they couple just to each other, which then means that if you do it reverse, integrate over the Hubbard-Satonovich field, you again write it. Okay. So you can consider just the general case where we start out from some theory which has an interaction operator, or an interaction term.
which is quarking in the fields, which as said here can now be bosonic or fermionic.
So consider general interaction term as int gamma delta. Let's just consider such a general term where now here in the rest of what I'm discussing I will always use a convention that I sum implicitly over repeated indices, okay? So summation over repeated indices. This here implicit, just to save some work. That's implicit. Then, as said, this psi bar of psi can be bosonic or fermionic field variables. And finally the variables alpha, beta, gamma, delta are some unspecified set of quantum numbers and Matsubara frequencies, set of quantum numbers like spin and momentum in the case of the electrons that we considered, and also contain the Matsubara frequencies. And finally, the V is just the general interaction potential. So actually, more precisely, it's the interaction matrix element. So the matrix element of the interaction operator with respect to these states characterized by the general quantum numbers and interaction matrix element. Okay, so this is like the most general scheme you can start out from, any interacting theory between electrons and bosons, and then we can just generalize of what we've done here. So the first step, what you do in this Hammett-Saltonovich decoupling is introduce some composite operator or variable which is, again, we'll come back to this, but this is motivated only by physics, okay? So this is the idea that we said, well, in the perturbation theory we saw that single electron lines didn't play so much role, but only composite objects. So here in this case, you can, for example, introduce rho alpha beta, which corresponds to C alpha beta. Now, because this is a composite object made of two elementary fields, this will always be bosonic. Okay, so it's bosonic, of course, if you start from bosonic theory, but also if you start from the fermionic theory, because you have two of them, this is always bosonic. And then what you do, just you rewrite the interaction, then in terms of this variable there, then you have summation over repeated indices implicit, so this interaction term then just could be written as density alpha beta times gamma delta. Now, just to simplify notations, let's introduce some different notations. So the notation can be further simplified. By introducing so the composite indices. So we call just M the tuple of indices alpha beta, and we call N the tuple of indices gamma delta. Okay? So if we do so, just to simplify notation, we can write interaction as a rho M, V and N, rho N. Okay? Now there is one comment I should make here. You see that okay, here again is summation over M and N implicit. So you see this is just a symmetric form. So even if you start out from a V not being symmetric, you can always symmetrize this. Yeah? So we can always assume that the V is just symmetric. So this was the first thing. Then the second step is to introduce the unit. Introduce a representation of the unit. Introduce in terms of some Bosonic field. Which we wanted to call phi. So we write the one. Integral d phi function integral. We're now take the following. So 1/4 again is just for later convenience. And the way we do it here is not the unique way you can do it. You can do it in different ways. I'll comment on that. So we just write again the unit operator in some complicated form, where again we absorb the normalization factor, the determinant here in the measure. Okay, just to make the notation simple. And just one thing that you should be careful. So the v to the -1 mn could have here, as I wrote it, two meanings. What I mean here is that it's the mn element of the inverse matrix. Okay, so that's here. And then what we do is we multiply the initial theory, which was had an interaction term e to the power of this here. We multiply by the unity. So and then multiply e to the minus rho m v and n rho n. Okay, so we just take this here and multiply this by this representation of the one operator. So just combining this. This was the second step, and then in the third step, what we did is we have to shift the field phi in such a way that we get rid of this interaction term. Third step, shift the variable phi m in a very specific way to get rid of the interaction term. Okay, so here actually this is a matrix multiplication, no? So if you write this in detail, this is V m n rho n. Pmn rho n sum over n. Okay? And this is chosen exactly such that the quadratic term in rho, which is actually, so it's quadratic in rho, but it's a quartic term in the original fields. So it's exactly the interaction term that makes all the problems, that this is cancelled. So what we arrive at is, after the shift, we can write the exponential of this interaction term, the quartic term in the fields phi, as a need to go over the fluctuating fields phi and phi, and then we have now, through the shift, eliminated this, and we have a coupling of the density, or of this composite object rho, to the fluctuating field. Okay? And I mean, in this integral we already assumed that V is symmetric. Okay, otherwise there would be two terms, but we said we can always assume that V is symmetric because it's actually described by symmetric form. So this is what we said what we are after, where the interaction term C bar C squared has been traded for by A, an integration over this auxiliary field, which is also called the Aula field. And B, we find that this is coupled, this Aula field is coupled to a psi bilinear, so the microscopic degree of freedom couples like a bilinear term to it. So here it was rho n. Okay, so this is the generalization of what we did for the one example. So one can always, for any kind of interaction which is quartic in the microscopic fields, do this trick. And then we just make some more comments, which already said. So if you look at it from like a mathematical point of view, it's just something very simple. So you think, why the heck do you do so much? Why do you give it a proper name? In the end, you're just talking about a simple Gaussian integral. So in essence, Electron-electron is just a simple application of the Gaussian integral identity e to the 1/2 ZAZ. So quadratic term can be written as constant times an integral dx e to the -1/2 xax. I just write it here in a way that is just reflecting how we did it. So I don't know where it is. So I write whatever it is. So I mean, we're just talking about a very simple identity. Yeah. So in a way, the quartic term you organize in pairs, in two pairs, product of two pairs of composite objects. So this would be the rho. Rho squared means C bar of C squared. So that's the interaction term. We write this as an integral over some new variable x, which would be the phi, where now the x couples to this rho composite object. So it's just a very simple Gaussian integral identity. Okay, so what we're doing. So mathematically, this is not so interesting, but to make it interesting, we have to fill it in with physics, and this has all to do with how you choose this composite object, and this we'll discuss in detail. So let me just continue here with some more comments. So mathematically, this is really, like when I saw it, I think like, what is the big deal about it? But see? So then, as I already said, there's a lot of freedom how you actually do this Hubbard-Satonovich transformation. I'll just write down some example. How to, so there's freedom how to exactly you do the decoupling, how to apply the Hubbard-Satonovich. So, for example, here we have chosen a factor 1/4 and n minus bn. And instead of the factor 1/4, you could have also just chosen no prefactor I don't recall. How did we choose it? Did we choose it with 1/4? Probably no. But then when you do the shift, you should do the shift. So how did we do it? We did it with a factor 1/4 and then just the shift without prefactor, I guess, no? Or with a prefactor 1/2. So we did it with 1/4 and the shift was a factor of 2. Yeah. Let's see. Okay, so of course you could do instead of the factor 1/4 and then with the factor of 2 here, you could just use here no prefactor and then here prefactor 1/2 probably. Okay, so this is one thing. Then another thing we have chosen here. The v to the -1, and then used in the shift that it's not there anymore, but we multiplied rho, so we shifted phi by phi plus v times rho. Okay, so phi was shifted by phi plus some factor here, v times rho, and this v then appeared twice to compensate for this white v to the -1. Okay, so we could have also started out from 1/2 phi, then here already chosen the v, and then in the shift not used anymore the v, just but the rho. Okay, you know what I think I'm explaining that, but it's trivial things that I'm saying here. It's just there's a lot of freedom how you want to do. So what we did here, let's write it like this way. And then we shifted phi by 2i, by phi plus 2i rho. But you could have also, let's say, started out from vn and then shifted phi by phi plus I rho, simply, okay? Now, there's a lot of freedom how you can do it. Now, what we have done actually is, in a way, yeah, I shouldn't have quite in a way, but what we found is that, no, it's still here, that after the shift, we have here just a factor I, and there's no v's appearing and no factors appearing. So if you would use, for example, this shift here, then here would be a v, but also here would be still a v. So a good way always to do the shift is such that here, which in the example that we discussed with the electrons was just the density, couples in the simplest way to the fluctuating field, okay? So if you would use any other choice, mathematically you can do it, but it's very convenient to choose it in a way that, as we saw in the electron case, we have just the, like what you would arrive at after minimal coupling of the electrons to some fluctuating scalar potential. Okay, so we want to often, or I think the best way to do it is such that we make this term the simplest. But as said, it could have here a V, and then there would be a coupling of the density not to phi, but to the potential V times phi. But it's more natural to keep it this way. Okay? So this could be, could have used also this one. Here we use the way such that the coupling of the fluctuating field to the microscopic degree of freedom, which was here phi and rho m, just with some factor I, is maximally simple. So that's often a good idea to try to do it this way. But mathematically, again, there's a lot of freedom. Then the final comment I want to make is that the Hubbard-Stratonovich transformation as such is just a mathematical identity, so it's exact. Okay? But then, what I try to emphasize all the time, like if you look at it mathematically, it's a boring thing, but it gets interesting once you make it really meaningful by filling it with some physical content. So however to make it meaningful, or to make it really something powerful, so meaningful I could also say to make it really powerful operation. It must be motivated by physical considerations. So that's the point where it gets interesting. Physical considerations. Hubbard-Stratonovich as defined as exact. However, to make it meaningful, a meaningful operation, it must be motivated by some physical considerations. And this is what we want to discuss, like in the rest. But just let's just comment and then we make a break and then we come to this. So all this is exact, nothing special, but we did something, and this is, we made a specific choice of the rho. So if we go back to the B, to the two-tuple index, we introduced the rho alpha beta as a psi alpha, psi beta. Okay. So we started from the interaction being B alpha, beta, gamma delta, psi bar alpha, psi beta, psi bar, gamma, psi delta. So what we did, we said, well, let's take this as a unit. They're close by to each other, so let's take this as a unit. But there's no reason why, like mathematically, why we should use these two. We could have used these two as a pair and these two as a pair, but we could have also used these two as a pair or these two as a pair. So at the beginning, we just have three ways to do it. And mathematically, we don't care the way we do it because all this is exact. So we can do it in either way. It's an exact mathematical manipulation, so who cares? But the thing is that as far as we're doing something exact, okay, nothing happens. But at some point, we cannot do any more exact calculations because we know we're starting out with some problem which is not solvable. So just changing the variable doesn't make it solvable. So the entire idea is that, well, this looks like something very simple to do, but there's a lot of physics entering here, and this is in the right choice of how you exactly do the decoupling. So there all the physics enters, and this normally can be a very tough problem. And like what normally always we said goes in the first step of the big program, so in the 5-step program, the first step was always try to identify some relevant structural units from perturbation theory, okay? So there you make an analysis of diagrams, and you should see, like in the weakly interacting electron gas, that some units might be physically, but just from physics point of view, more dominant than others. Like there can be some phase-based argument that certain scattering processes dominate over others, like in the big, large density limit. And this then tells you that there are certain composite objects, like the density in the weakly interacting electron gas, which tells you the way how to do it, okay? Now, this is a very important step, and this can be very complicated, and sometimes it can be that you shouldn't decouple just one way, but you have to decouple in 2 ways simultaneously and whatever. This can be very complicated. But the statement that I want to make here, and which is important, is that mathematically you can do it either way. You have an identity, you arrive something, and then you're with this. But then the point is that what you're stuck with now, you want to derive from this low energy field theory. So you do some saddle point analysis and look at fluctuations around it. If you chose the decoupling in a wrong combination, you will never succeed to derive a meaningful effective theory. So all the information is stored still here because it's a mathematical identity, but the art is to make the decoupling in such a way that then you can just derive an effective theory. There's a controlled parameter, how you can make an expansion in the fluctuation of this new degree of freedom, which is controlled and which keeps the physics. So if you make the wrong decoupling, the identity is accepted, and if you try to make an effective theory, like expanding in fluctuations, you will see that there's no controlled way to do it. So all the information is there, but you should go to infinite order in the fluctuations to get the physics that you want. So the big art is to make the decoupling in this way, that you have the physical content, which allows you then to make a controlled derivation of an effective theory, that the low order expansion in the fluctuation of this field keeps all the physics. And this can be, like in the examples that we discussed, it's simple still, but this can be arbitrarily complicated, like if you have more than one order parameter or order parameter that are not clear at all, that took like a long time to identify. This can be really hard. And this is like where the thing also gets interesting, no? Because I mean the mathematical identity is like high school. Okay, it's not interesting. But this is the interesting part, and this is what we try to discuss in more detail like in the rest. So let's make 5 minutes break and then we can come back to this. Okay.